Continuing on with anti-differentiation by substitution, or the substitution method, we're going to go ahead and take a look at the Marauders map. The Marauders map was a magical document that revealed all of Hogwarts School for Witchcraft and Wizardry. Not only did it show every classroom, every hallway, and every corner of the castle, but it also showed every inch of the grounds, as well as several passages that were hidden within its walls, and the location of every person in the grounds, portrayed by a dot. It was also capable of accurately identifying each person, and the map was not fooled by animagi, polyjuice potions, or invisibility cloaks. Even the Hogwarts ghosts were not exempt. So let's suppose that the path of Albus Dumbledore can be traced using the equation 0 to x of tangent t secant squared t dt, where xy is a coordinate on the map. Okay, so for this one, we're going to have to learn a little bit more about substitution. Let's take a look at this one. We have the integral from 1 to 2 of x multiplied by the quantity of x squared plus 1 cubed dx. The approach we're going to take here is to find the antiderivative first. So let's find the antiderivative. We see here we have a polynomial to the third power, also multiplied by x. Now the polynomial to the third power is x squared plus 1, and if I take the derivative of x squared plus 1, I get x to the first power, which is conveniently similar to the other polynomial outside the cube. This kind of leads us to thinking that we could use u as x squared plus 1, and that kind of makes the x and the dx part of the du. Now, if u is equal to x squared plus 1, then du is 2x dx. We don't actually have to substitute that 2, or we don't need that 2. So we'll just divide that both sides by 1/2. And that tells us that we can substitute x dx with a 1/2 du. Moving on to the problem, we're going to regroup. So we get x squared plus 1 cubed, and then multiplied by the quantity of x dx. Then we make our substitution, where the x squared plus 1 becomes u, and x dx becomes 1/2 du. We can integrate this because it's just the integral of 1/2 u cubed, and that gives us 1/8 u to the fourth power plus constant, which is just 1/8 x squared plus 1 to the fourth power plus constant. So now that we have the antiderivative, we're just going to work with the fundamental theorem of calculus, which means we're going to substitute the upper and lower limits into the antiderivative. So substitute the lower limit, substitute the upper limit, and that should get us to 609 over 8. This is going to be the method that we use with the substitution method for lower and upper limits, or for a definite integral. We can just find the antiderivative using the substitution method, and then use those antiderivatives for the fundamental theorem of calculus, which is basically what we do anyways. Now, there's also something else that we can do here, which is called a full substitution, or a complete substitution. And when we make a complete substitution, we're going to substitute the lower and upper limits, and we're not going to look back. So suppose the path of Headmaster Albus Dumbledore can be traced using the equation y equals 0 to x tangent t secant squared t dt, where xy is a coordinate on the map. What is Dumbledore's location when his x-coordinate is pi over 4? So, first thing that we're going to notice here is that in our integrand, we have a tangent and a secant squared multiplied with each other. We know that the derivative of tangent is secant squared. So this is going to suggest to us that u is going to be tangent x. So given the integral that we started off with, y is equal to the integral from 0 to x of tangent t secant squared t dt. We want to find when x is equal to pi over 4. So we substitute pi over 4 into that upper limit. We say that u is tangent x and du is secant squared x. That's just the regular substitution method that we're using. But the complete substitution happens on the next line. When x is pi over 4, u is going to be the tangent of pi over 4, which is 1. And then when x is equal to 0, u is going to be equal to the tangent of 0, which is 0. We're going to substitute those upper and lower limits into the integrand. And notice now the integrand and the limits, everything is in terms of u. So we don't ever have to go back to tangent and x and all of that. We'll just do everything in terms of u now because we have completely substituted all traces of x out of the problem. So when I integrate u du, I get 1/2 u squared evaluated from u equals 1 to from u equals 0 to u equals 1. The next thing to do, of course, is to substitute. Remember, we're not going back to x. We're just keeping this problem the way it is because everything is in terms of u already. So we have 1/2 of 1 squared minus 1/2 of 0 squared. That's just 1/2. And so Dumbledore's location is pi over 4 and 1/2. The key step here is to substitute for the upper and lower limits, and then, like I said earlier, don't look back. Don't go backwards. Don't go back to x. There's no reason to do it. A lot of times this will simplify the integrand so much because you're left with a polynomial function. The other added bonus here is that the completely substituted integral is often what you're going to is often going to be what you see in a multiple choice test. So kind of get used to looking at this complete substitution because you will see it as a multiple choice test. Even though it is kind of an optional step, I highly recommend you work on it this way. So that was a pretty short lesson. So I have a feeling that these check your understandings are going to be a little bit more difficult. So we might spend our time here. So a few thoughts. Number one, when you're using the substitution method, you need to make sure that you actually need to use a substitution method. Not every integral requires it. In fact, we spent a long time doing integrals without even the knowledge of basic integrals. So don't feel like you have to use the substitution method for every integral. Now you have two options here for definite integrals. In the first one, you can evaluate the antiderivative and then just substitute the upper and lower limits like normal. And then for option 2, you can make a complete substitution where not only do you substitute into the integrand, you also substitute into the upper and lower limits. I had mentioned that option 2 is often used in multiple choice questions, so make sure you're aware of this when you're taking a multiple choice test. Let's take a look at Check Your Understanding A. We've got the integral from 3 to 5 of x over x squared minus 4. And I'm going to pretend I didn't see what the hint is. But looking at our integrand, sometimes the entire denominator is going to be your choice for u. So my entire denominator is x squared minus 4. And if I take the derivative of x squared minus 4, I get 2x. Now 2x, the 2 is not important. What's important is that I get that x. And the numerator of this is x dx. So I think that will be sufficient for a substitution since all the important parts of the derivative appear in the integrand. Making our u substitution, we know that if u is equal to x squared minus 4, du is going to be 2x dx. And to make this substitution easier, I'm going to say that x dx is 1/2 du using some simple algebra. Substituting for those upper and lower limits, when u is equal to 3, the lower limit, when x equals 3, the lower limit, u is going to be 3 squared minus 4, which is 5. And when x equals 5, the upper limit, u is going to be 5 squared minus 4, which is 21. So we're ready to make a complete substitution into this problem. So the integral of x dx over x squared minus 4, that's the same thing as the integral of 1 over u multiplied by 1/2 du. Notice also that the integral limits have changed from 3 to 5 to 5 to 21. This gives me the natural log of u from 5 to 21. Incidentally, I checked that the u's, 5 to 21, those are all positive numbers. So anywhere in that range from 5 to 21, I'm not in danger of substituting a negative number into a natural log. So I don't need the absolute values. We get the 1/2 the natural log of 21 minus 1/2 the natural log of 5. Using some log properties, we know that we have this natural log of the square root 21 minus a natural log square root 5. And then using even more log properties, this is a natural log of 21 of root 21 over 5. So that kind of, the total substitution here definitely made things easier. I didn't have to go backwards and, do all of the arithmetic from substitution. Moving on to part B, on my denominator, I have a square root of y plus 1. Now, the inside of a square root is another place to look for u. So if my u is y plus 1, my du is just going to be equal to dy. So there's not going to be any real cost to making this substitution. So let's make that substitution. That's not that bad. It's pretty easy. So our first step here is u is y plus 1 and du is dy. Next, we're going to substitute 0 and 3 into our equation for u. So we have the lower limit goes from 0 and it becomes 1 when in terms of u. And the upper limit in terms of y was 3. 3 plus 1 is 4, so the upper limit is 4 in terms of u. When I make my substitution, I'm going to get the change from dy over root y plus 1 into du over root u. And then the upper and lower limits change from 0 to 3 to 1 to 4. The next thing I could do to make this easier is instead of du over root u, I consider the integral as u to the negative 1/2 power du. This antiderivative is just 2 u to the 1/2 power, and so we're going to evaluate from 1 to 4. Again, not looking back. Don't substitute back for y because we've turned everything in terms of u. We substitute 4 and 1, and that just gives us 2. So there was a lot of little bit of tricks and hints sprinkled in there about what to look for in terms of u. I talked about the denominator. I talked about inside the square root function. I also talked about sometimes a whole trig function could be your value of u. So keep those in mind as you keep practicing the u substitution. I know you're going to do great, and we will see you next time.